Hi everyone and welcome to CS50 Week 5 section. Today we're talking all things data structure. My name is Julia and I'm a preceptor here on Harvard's campus. And today we're going to talk about data structures, linked lists, hash tables, and we're going to walk through the inheritance problem that is one of the problems on the problem set. Well, let's talk about data structures first, right? We've covered variables, we've covered arrays, which is like really our basis for all these data structures that we're talking about today. But what kind of operations you can do with them? Like, why should we use data structures? Well, some of the basics one that we will see today is deletion, insertion, and search, right? Some of the basic things that you can do even with arrays, and now that we're leveling up, so we're graduating to linked lists and hash tables. There's another way of arranging it, right? Was like search, insertion, or deletion, or even insertion, search, and deletion. So we will cover how to create linked lists, how to insert elements into linked lists, and how to delete linked lists today. But what are linked lists, right? So they're really the nodes that we connect together in this little train or chain of elements. So in a very similar way that we had arrays, right, having like cells stacked right next to each other, linked lists are very similar. They're just a little bit like more layers of how we connect them together, namely using pointers, right? So recall from the previous week, we've talked about pointers, which is another data type that stores the addresses of other variables, and we can use them in a very nifty way to reference the variables between each other. So even here in linked lists, we use pointers to point to the next element in the linked list, and in such a way keep track of where the elements are and where we are in those linked lists. Graduating from linked lists and going a little level up again are hash tables, which combine the arrays and the linked lists all together. So you can even imagine it as having an array, like a vertical around the side, and then linked lists coming from each bucket from it. And we'll talk more about how to set up hash tables and how they actually work. One of the other data structures is trie. So it is sort of similar to a linked list, but like slightly different. If in a linked list, we, for example, stored one phrase in one sort of like cell, part of the node, in trie, if we want to store the phrase, each sort of like circle in this diagram represents one character. And so, for example, if I wanted to grab the word hello, I would have to trace all the way through HELLO. But again, since, for example, hey has the same two first characters, instead of writing hey all over again, I can just trace it using the first HE and then adding Y in the end. We're not going to touch on tries in this section, but you're certainly welcome to explore that on your own. So let's again sort of bring it down, right? Like let's start from the very bottom. Let's talk about how can we go about building these linked lists and what are some of the components that go into it. The first thing we need to consider are nodes, right? So as you saw in the first slide, we had these squares that represented the elements in the linked list, also called nodes. So how do you go about creating them? This is where we reference now week 3 concepts when we talked about structs, right? So even though linked lists and hash tables and even the concept of nodes is very common in the CS world, we still need to define this data structure ourselves. So recall that as last time, we have type def and struct and then the name node on the bottom. Now though, we want to ensure that we can just reference this data structure as node, right? Like we don't want to write struct node every time. So therefore we're adding another node word on the first line. So that will allow me to just type node whenever I want to create a new sort of like element in my linked list. Then what we have is the middle parts, right? Like our attributes or components of our struct. And again, they can be whatever you need them to be depending on what linked list you're creating. Today, we're going to talk about linked lists that just contain a phrase or word in the first part and then the pointer component on the bottom. So now we're just creating an attribute string phrase that will contain some word. And now to the newer part, right, that we didn't really see in week 3 and where we're actually using pointers is the next component. So notice how the first bigger part is the phrase and then the bottom part is next. And then from the code on the left, we can tell that it is actually just a pointer to the next node in the linked list, right? And since it is a pointer, what does it store? If, for example, phrase stored a string or a word, what would next store? An address, exactly. So pointers store addresses. So next we'll store some sort of address, right? We're still using these like fake addresses right now and it will look different in computer, but it can be something like this or something like this. And it will point to the next node in our list. And again, kind of like bringing it all back together, this is how our code will look like. Using typedef and the struct definitions, we can create our own customizable nodes to use throughout our code. Okay, let me take a quick pause here and ask what questions do we have so far about node definitions or anything else. And we're going to debunk it further as we're learning different operations to do with linked list. But what questions do we have so far? All right, seeing none, and we'll definitely can come back to this, but let's keep moving and let's talk about how we can go about creating a linked list. Well, the first thing that we need to do is to have a pointer that is always staying on in the beginning of our list, right? Like this is just our reference point that we'll always use to determine where the beginning of our linked list is. And again, we will use the pointer notation so we know that the list variable will point to a node or sort the address of that first node in the list. And for now, we're just pointing it to null because we haven't created anything, okay? Next, what we want to do is create this node, right? We want to allocate some memory, and this is where malloc and sizeof comes into play again. So using the sizeof function, we can determine how much memory do we need to allocate for that node. And again, sort of like going back to our slides, since we've predefined the data structure, the computer will know exactly how much space each node needs. So since we've already, again, defined the struct node, we can use this line of code to create sort of this like empty box, right? That will be our first node so far. And since we are, again, using a pointer to store the address of this node, we will have variable n that is pointing to that element of the list. Okay, next what we need to do is populate it, right? So we said that each node will have two components, the first one being a phrase, so in this case, hi, right? And then the second part is having a pointer to the next node. Well, we don't have a next node just yet, so we can just set it equal to null. And this is where we have slightly different notation. So recall that in week 3, when we wanted to access the attributes of a specific struct, we used a dot, right? In this case, we're using an arrow because it is a pointer to the next node, right? Not just like an attribute or like a variable that we're trying to access. So same concept, we're still accessing the attributes inside of our struct, but because they're pointers, we want to make sure we're using an arrow. Okay, and lastly, what we need to do, again, we said in the beginning that list has always to point to the beginning of our linked list. So what we're going to do, we're going to reset list to point where n is currently pointing, doing such, and now we have list pointing to the very first element. Let me show the full screen. So now list is pointing to the very first element and keeping track of where we are. Okay, so this was creating nodes, right? Again, sort of like an algorithmical approach to it where we want to make sure we are allocating memory, we're populating our struct in the correct way, and we're always keeping track of our first element and for the next elements to come that we'll see in the next part right here. Okay, let me go through the next chunk and then pause again. So now let's talk about inserting nodes, right? We will definitely have one and more node to deal with. So how can we go about actually creating this linked list, right? Not just one node at a time. Well, we're going to do something very similar that we just done, right? We're still going to use malloc, and we're going to use size off to create a new sort of like empty box. As before, we're going to populate it with a phrase. So for example, hey, and then because we want to keep track, right, we want to connect these nodes now, right? This is where the whole concept of linked list comes into play. What we're going to set and next to is to where the list is pointing, right? So recall that before, list pointed to where our first node was located. So now we want to grab our new node and point and next to where the list was pointing to previously, right? So creating this connection between the two. And now, since we always want list to point to the very first element in the linked list, we need to make sure we reset it, and now list will be pointing to hey and not hi. So see how technically under hey, in this like second part, we don't really have anything stored, but what it really is storing is the address of the node hi, right? The one that we have on the right-hand side. So this is how the two of them or three or however many get connected. List variable, or again, however you choose to call it, will always sort of like store and keep track of our very first node in the list, and all the subsequent ones will be connected through the next attribute, storing the address of the next node in the list. Okay. Let me pause here for now before we go into deletion part of linked lists and ask what questions we have so far. And while people are pondering, this is definitely, again, like escalating one more time as we've had things escalate over the past few weeks. So definitely take your time to draw it out on paper, rewatch section, rewatch lectures, and try to figure it out on your own as we're sort of like abstracting things away every week. But what questions do we have so far about creating linked lists, inserting elements into linked lists, or overall structure of nodes? Yes, the recording of sections are now posted on the Zoom page where you registered for this section. I've updated all of them so you can see the recordings there now. Okay, seeing none so far, so let's keep moving. And last thing that we want to talk about today is deleting the nodes, right? And recall from last week that anytime we use malloc, we want to make sure that we're freeing that memory, right? That we're giving it back to the computer, because we just don't want to run into any error, memory errors, right? Or like touch the memory that we're not supposed to. So anytime you malloc, make sure you free it and give it back to the computer. Well, just calling free is easy, but how do we actually do that on the linked list? So let's go back to what we had before, which is our 2-element linked list, right? Hey and hi, just 2 elements. Well, a very, easy way would be list is pointing to the first element, so I can just do something like free list, right? And get rid of all of that memory that I've allocated before. But what is the issue here? Why can't I just call free list and move along with my life? What would happen here if I just said free list? Any ideas? Let me maybe zoom out again. Exactly. So it will just delete the very first list, but we will lose track of what's coming after it, right? Like we're freeing our very first node, but what about high, right? Like now we don't even have any connection to the second node. So if we freed list, right? Sure, great, we gave back that part of memory, but now we don't even know where the high node is located, right? Like we don't have a way of accessing it. Therefore, we have to do something different. So let's reset again. And let's introduce this new variable. So very similar to the whole idea of swap that we saw last week, we're going to have the third variable that's going to be sort of like the intermediary between the two, keeping track of the next node after the one that list is pointing to. So let's walk through it step by step. We're creating this new variable called PTR or pointer, and it is going to point to the next node after the node that list is pointing to. And I know it's getting a little bit confusing, but let's try to visualize it. So if list right here is pointing to the node hey, right? List arrow next will actually go into this cell and grab the address of the high node. So actually what PTR is storing is the address of high node, right? So now, even if we delete free list, we can still keep track of what's coming after it, right? Because we are storing the address of the high node inside of PTR. So now that we've freed list, next thing we're going to do is reset again. So list has always pointed to the first element in the linked list. So now that we've got rid of the hey node, we need to reset. So grabbing the address stored in PTR, we're going to set list to point to the same node. And now what PTR is going to point to? Well, the next node, right? And even though there is no third element in the linked list, but you can imagine it is common to have more than two, what PTR is going to store next in this case is null, right? Because it will always store the address of the next node from the one that list is pointing to. And since list is pointing to high, we're going to go into this node, go into the bottom box, and then record null as the next thing that PTR is pointing to. Obviously, in this case, less interesting because it's just null, there's no next node, but we still do this operation. And then now that we free list, we get rid of our last element, and then we technically still need to repoint, right? Like we still need to reassign list, to assign list the address that was stored in PTR. In this case, it is null, so we can conclude that the operation was successful and we've reached the end of the linked list, so therefore we freed all the memory, right? But again, just very important that we're keeping track of every node that comes after the one that list is pointing to. Because if we don't have this third intermediate variable that stores the next node, we can very easily lose track of the rest of our linked list, and then we will forever sort of like lose that memory and run into some errors. So creating, even like taking up space and creating that extra variable, but to make sure that we are keeping track of what's coming next is really important. Okay. Let me take another pause here and ask what questions we have about linked lists so far, insertion, deletion, or creating a linked list. And we're going into the exercise shortly, so we'll actually see how to implement it all in code. But what questions do we have so far? Okay, seeing none, so let's keep moving. And let's talk about our first exercise. So in this program, what we're going to do, we're going to implement code that will add a node to the linked list. And we will also implement an unload function that will ensure that we're always freeing the memory that we are allocating. So I've already pre-created something. So let's open it up. Oops. All right. So this is our, let me close this guy. All right. So this is the code that we have so far, and let's just very quickly walk through it. So on line 6 to 11, we have our definition of the node, right? Exactly what we just seen on the slides, where we define exactly what node has to be, specifying the first attribute as phrase and the second attribute as a pointer to the next node. We're going to keep it sweet and short, so just a linked list of size 2. Don't worry about the visualizer function. This is just so that we can see what's actually going on behind the scenes. But unload will be the function that we'll create to make sure we're freeing the memory and giving it back to the computer. Next, what we have is our main function, right? So this is where we're going to change some things. So the first thing that we need to do is to create this first pointer, right? The variable list that will always keep track of our first node in the linked list. Next, we're going to use a for loop, right? Just to make sure that we're not repeating the code and not saying the same thing over and over. So we're just going to iterate through that 2 times. Creating a new node and adding some phrase to it. And then lastly, what we're going to implement is an unload function where we're going to free all the allocated nodes, right? So let's start filling out our to-dos. So the first thing that we're going to do is adding this new node to the list. And we're just going to follow what we just talked about on the slides, right? So we've already created the list variable that is always going to keep track of the first node. And you can sort of like imagine it sitting somewhere like on the left side, for example. What we're going to create next is allocate the memory for our new node, right? So to do that, we're going to create a variable n. We're going to use malloc and size off to allocate the exact amount of memory we need for the node structure. I don't think we've talked about last week, but also important thing to double check is, was the memory allocation successful, right? And a way to do that is check if n is equal to null, right? If for some reason malloc failed and the memory was in fact not allocated, we want to make sure that we exit, right? Because we've talked about that accessing any memory that we were not supposed to access or trying to access something where something went wrong, we want to make sure we're exiting and just restarting the whole process again. Now that we've created this new node, right? Like again, visualizing it all in your head, we have this box that has 2 parts. So the first part is phrase. So we need to populate it with something. So we're saying n phrase will be equal to phrase because that is what we're grabbing from the user on line 25, right? We're calling getString and asking the user to give us some word, for example. Our next node is literally, our next component is literally called next. So n next, we will set it to what? So as we're creating a new node, what do we want to set n arrow next to? So we've allocated some memory and we set the phrase. What are we setting n to point to next? Okay, the next address, the address is the last one, right? But this is our first node, right? Like we don't have anything else going on. So what do we want to set it to? This is our like very first element in the linked list. There's nothing else going on. Okay. I'm seeing some suggestions, but it is really just null, right? Because we don't have anything else going on right now, and we just want to set it to null to have some placeholder for that. Well, some of the suggestions that already came in the chat is what we're actually going to do next. So we're going to, oh, actually, I think I have a mistake in my code. And you guys might have been right. Let me see. Okay. Okay. So let's talk about why I made a mistake here. So the reason why we set it to null at first is because if we're creating the very first node, right, there is nothing else that we have in the linked list so far, so it is true that we have to point it to null. But recall that this is a for loop, right? So we're using the same algorithm to create all the next nodes. So in that case, we will indeed need to ensure that n arrow next is pointing to where list was pointing to. So let's get rid of this part and let's keep n arrow next equals list. And then as before, what we're going to do is repoint list now. So now that we set on line 35 to use n arrow next to keep track of the very first node that we created, now we can repoint list to where n is, so that we're always keeping track of the very first element in the list. So let's try to compile it and let's try to run it. So for example, Apple, and let me just make the terminal bigger. So note how when we created the first element, the next is still null. And the reason for that is since we set n arrow next equal to list, it's just going to point where list is pointing. And so far, list is just pointing to null. So actually, the very first line that I had was not necessary at all because it is sort of getting accounted for in the rest of the code, right? So it has some location, it is storing the phrase, and it is the next node is null for now. Well, let's enter the second phrase, for example, banana. And now what we see is that the second node that we actually created, again, comes to the top of the list. So it has some location, the phrase, but then note that whatever is stored in next is the location of Apple, right? So this is where this connection is happening. This is where pointers are super important because they're helping us keep track of the addresses of all the next nodes in the list. And note that the Apple node is still pointing to null, right? Because we haven't reset it to anything. Okay. So that was us creating a linked list. Now let's talk about unloading it, right? Or freeing it, because so far you can see that there was an error, right? Like we actually haven't freed it properly. So let's go into the unload function and talk about how we can do that properly. And to address that, let's actually go back to the slides for a second and let's see what happened here. So notice how when we're talking about this diagram, right, what was the pointer set to after this operation? Like if we write PTR equals list arrow next, what is the value of PTR after we run this line of code? What does list arrow next store? Or what does high node point to? Null, exactly, right? So PTR now will store null, and so we can move forward with that. We're freeing the list, and then we're resetting list equal to PTR. And after that, I claim that we were done, right? Like I claim that this was the end of our deletion process. And we can see that visually, right? Like we got rid of all of the nodes on the slide, so we don't have anything to delete anymore. But if we think about it in terms of code, what kind of condition can we set here to check that we've actually reached the end of the list and there are no more nodes to free? What kind of condition could that be? Okay, so some people are suggesting like a while loop. That's a good intuition, but what condition do we want to set? Like, right, what Boolean expression do we want to put inside of that while loop? Yeah, exactly. So if PTR is equal to null, like, or list equal to null, we're done, right? So let's go back to our code and try to, again, code it to see what's going on. So as on the slides, we're going to create this new variable, right? The third intermediary variable that we're going to call pointer, or PTR for short. And we're going to set it to where list is pointing to, right? Just keeping it simple for now. Again, it's slightly different from the diagram, but bear with me as we're going through the code. Then we're going to have some kind of while loop, and let's leave it blank for now. But inside of that while loop, what do I want to keep doing repeatedly, right? Like, what is the same steps that I want to do every time until I reach a certain condition? Well, that would be setting PTR equal to list arrow next, right? Like we always want to keep track of the next node after the one that list is pointing to. So since we're in the while loop, we want to make sure that our conditions, sort of like our steps, are uniform, right? Like standardized at every step of our process. Next, we're going to free the list, right? So we're keeping track of what's coming after this so we can very securely just get rid of that block. And then next, we want to repoint list to where PTR is, right? So with these three steps, we can keep going on and on and on and on in the very same format until we've indeed deleted all of the nodes. So first, creating a PTR variable, and we can set it to list for now. You can set it to null, it doesn't really matter. That inside of the while loop, we are going to repeatedly set PTR to sort of like the following element, the next one over every time. Since we're keeping track of what's coming after the list, we can very safely just remove that piece. And then we're going to reset list to where PTR is pointing, right? So we're always sort of using this like swap method and using this third variable to keep track of what's coming next. And as someone suggested in the chat, what is the condition where we want to stop? Well, while PTR is not equal to null, we want to keep going, right? So while we haven't reached the very end, we want to keep going. So now that we have this part, we can set this to true. And let's try running it. So let's do make list. Oop. Let's try running list, banana, apple, and then let's see what's going on the bottom, right? So we've had our two nodes inserted. So apple is keeping track of where banana is. We freed the list since we've gone through all of these steps. And now we've successfully gave back memory back to the computer. Okay, so beyond sort of, like the operations that we just talked through on the slides, it is also important to make the steps sort of like standardized, right? Like if you're using a for loop or using a while loop, if you're using a while loop, like at every stage, you want to make sure that you're using these like standardized steps because you don't want to write the same code like 10 times, right? Like we want to make sure we can just use that iteratively. So like a mistake that I made in the beginning was that, sure, I could set an arrow next to null when I'm creating my very first node. But since I'm in the for loop, I don't want all of my nodes after that to be set to null, right? So again, some like logical considerations that you also need to make as you're writing your code, just beyond, like the operations or algorithms that we talked about on the slides. Okay. So let me take a pause here before we graduate to hash tables after and ask what questions do we have about linked lists so far. What questions might we have? Yeah, so someone asked, what is the relation between the address of apple and banana? So recall that banana was the first node that we created, right? So that's why next is just null. And then everything that we create has an address, so that is what the location is. Next, we've created apple, right? And it has its own location, but this is where the connection between the two happens, right? The location of banana is what gets stored in the next part of the apple node, right? Like this is our link. This is what makes it a linked list. We can keep track of the nodes by using pointers. Okay, let's keep moving then, and let's talk about hash tables, right? So this is something that we just saw, which is a linked list, right? And we can connect the three of them together, right? Just using the approach that we just did, sort of like corresponding them with each other using pointers and the addresses that they have. But say, for example, if I wanted to look up hello or like hello there, right? Like it will take me some time to go through each of those components in the linked list looking for that element. And this is where hash functions or like hash tables, right, come in. They allow us to create some more space and some more organization to search elements in a better way. And actually, hash tables, right, are very efficient in searching because ideally each bucket has one or maybe just a few of those elements. And so looking things up is very easy, right? But visually right now, and as a human, I can say, okay, hey corresponds to the bucket H, low there corresponds to bucket L, for example, if we're just using the alphabet. Like if you're using some other greeting, like this is where it's gonna go in, but the computer doesn't really see like alphabet, right? Or like there is no sort of like organic or semantic sorting that it can do. So what it actually uses instead are indices, right? And so in this case, we can imagine that it is just the alphabet. So there are 26 in the English alphabet, and so there are 26 indices, and this is how the computer is assigning all of these nodes. But in an efficient hash table, we can have hundreds or thousands of these buckets, and this is again where some of the trade-offs or considerations come in, right? Okay, you can create like a hash table of like 1 million buckets, right? And then maybe your elements will go into one bucket each, and so it'll be really easy to look it up. But then you're taking up so much memory using that 1 million buckets. But on the other hand, if I just create 5 buckets, right, all of my words will get clumped together, and so I will still need to go through each one of them looking for the word I actually need. So there is some, consideration or min and maxing that you need to do to ensure that you have a good number of buckets, but you're not using too many or not enough, so that it is eventually still inefficient. But how does computer actually assign these indices? Well, we can use hash functions for that. And in fact, hash function is some kind of algorithm, and there are many that exist out there in the internet, and we're going to talk about one of them and how to implement it. But hash function is just something that can take a word, right, or phrase of what you want to store, and then give you a corresponding number or a corresponding index of the bucket where you want to put that phrase or word into the hash table. So for example, if I put hey into a hash function and it gives me back 7, I'm going to then go into the bucket with index 7 and I'm going to put hey in there. Okay? So let's talk about hash functions, right? Like, how do we implement them? And let's talk about a very simple one. So we're going to create a program where it already has some of the pertinent components, but our goal was to create a function that can give us that number. So let's go back to cs50.dev, and I'm going to close this tab, and I'm going to open a new file. All right. So as before, I've already written some stuff here. I have my libraries, I've defined my nodes, some functions. Let's take a closer look at main. So what we're doing here, we're just prompting the user to give us a phrase 3 times, and then we're going to use our hash functions right here to determine what bucket it belongs to. So our goal was to create a hash function that returns a number from 0 to, oh my goodness, why is it jumping? From 0 to 25, depending on the first character of the phrase, okay? So we've talked about alphabet, right? And now we're talking about 0 to 25. So what approach might we want to use here, right? Like, what exactly will 0 to 25 number signify here? How might we want to approach this? Yeah, so we can use ASCII codes, exactly the alphabet. So essentially what we want to return is the sort of like the location of that letter in the alphabet, right? For example, if I have apple, I want to grab character A and I want to return 0, right? Because it's the very first element in the alphabet and we're always starting counting from 0 in CS. So if it is banana, I want to return 1. If it is carrot, I want to return 2, etc. But again, it's not something I can just tell like, oh, return the corresponding index of the alphabet, right? The computer doesn't know that, but it does know ASCII. So this is where it becomes very powerful. And sort of like similar to Caesar, for example, we want to make sure we reset, right? So the, what is it? The uppercase A ASCII code is 65. I think. So we want to make sure that it's not returning 65, but it's returning 0. So we always want to kind of like reset. So let's consider this. Maybe we can just do phrase 0, right? Always grabbing the first character of our phrase. And then I can do something like minus A, right? And because my hash function returns an int, it will know that will have to be an integer, so we'll do some ASCII calculation on the background. But what might go wrong with this approach? I would argue that I'm missing one important part that will truly make my hash function uniform. What is my main assumption here? Exactly. My main assumption is that it will be all uppercase, but what if it's not? What if I'm like, one is lowercase, one is uppercase, then I'm mixing it up, and then I'm getting all the different numbers back? That's not what I want, right? Like, if I type apple, no matter if it's lowercase or uppercase, I want to make sure I'm always getting the same value back. So one thing that I can do is just use toUpper to convert any character that I get to the uppercase letter and then subtract A. Okay, so let's try using this. So let's say make table, and we need to include the library since we're using a different function. Okay, let's make it again. Let's clear this. Let's run it. Okay, so if I run table and I say apple, I get 0. If I say uppercase apple, I also get 0, right? And if I say something like, oh my God, what are other words that start with A? Antidote, I don't know what that came to my mind. That also hashes to 0, right? So we always want to make sure we're grabbing the first character of our word, no matter if it's uppercase or lowercase, and we're hashing it to 0. Again, like this is where we can consider some trade-offs, right? Or considerations like, if I only have 26 buckets, like that's probably not the most efficient one, because like you can imagine how many words that start with A exist out there, right? So if they all hash to 0, what I'm gonna have to traverse through my entire linked list, which can be thousands of words, just looking for one. So again, there's like, this is the part where you can consider how many buckets should I create? Like if I'm storing, for example, a dictionary of all the worlds, like of all the words, is 26 buckets enough? Probably not, right? Like you want to go higher. Should you create like a couple of millions of buckets? That might be too much, right? Like you might be taking too much memory with that. So some of the things to consider here. And let's talk about one more option that we could do here. So if I instead had something like this, would this produce the same results as the previous line of code? Will I also get 0 for apple if I do this? Someone said yes. No. Okay, I see no. Let's try it. So let's make the program again. Let's run it. I say apple, and I get 0. And then I say apple, and I also get 0. So the reason why it is working is because I'm just keeping it consistent, right? So in the beginning, I just set it to the uppercase, and then I subtracted uppercase A. Here, I'm sort of doing the opposite, right? I'm first converting it to the lowercase character, the lowercase letter, and I'm subtracting lowercase a. So it is sort of like ensuring that even if I'm changing things a little bit, I'm still moving within the same boundaries, right? Like I'm not converting it to lower and then subtracting the uppercase like C, right? I am doing sort of like this, the same thing, but just in a slightly different way. And then for demonstration, let's type that word. It's also hashes to 0. Okay, so there are lots of different ways to come up with these hash functions. This function is arguably not the most efficient one, especially if you're dealing with a lot of information. But again, this should give you some idea of how it can work. Well, now that we've talked a little bit about hash functions, what is a good hash function, right? Like what ensures it, that it is like efficient, right? Or like giving us the results that we want. A good hash function will always give you the same value for the same input, right? So no matter if it was like lowercase apple or uppercase apple, it gave me 0. Like if I want to run my program again in like 3 days, I still want to make sure that it's giving me 0. So even if you're using some randomization inside of your hash function, you want to make sure that it's uniform. You want to make sure that it's even distribution across all the buckets, right? So in the case with the alphabet, there is more like a stricter consideration, like it's just depending on the first character of your word. But there's a way to make a hash function that will just put words randomly among all the buckets, but it will still be very like deterministic, and it will give you exactly the value that you were expecting or got in the past. And sort of like similar, it will use all of the buckets and have the even distribution among them all. Okay, so let me pause here and ask, what questions do we have about hash functions? Hash functions or hash tables, right? Like how we combine those two things together. All right, seeing none. So let's move to our last part of today, which is talking about inheritance. And if you haven't looked at the problem set yet, it is one of the problems that sort of like combines the idea of linked lists with recursion, which we talked about some weeks ago. So let's go back to CS50.dev, and I'm going to switch the tabs. All right. Let's clear this. Let's close this tab. And let's briefly walk through the code. I'm not going to comment on every part of the code written, and you're definitely welcome to read this back afterwards. But the gist of it is that we want to create a generational tree. And we're going to have a very custom struct that I'm going to talk about in just a second, but essentially it is two parts, where in both parts it is an array of two elements, one of them that is just storing characters or alleles, blood types, and the other one that is pointers to the parents, right? So we've talked about linked lists, we talked about try a little bit, but this is sort of like an idea of like a tree where it is coming from top to bottom, and it's filling it out with the pointers that point to the bottom nodes. There are some functions we're going to go over. The main function where we sort of like consolidate all of the smaller functions, the helper functions that we write. So essentially, the goal is to create a family, to print it out so that we can visualize it, and then to free the memory in the end. The create family function is where we're going to spend most of our time today, and let's talk about it in more detail. Notice how the function has a return type of person pointer. So what this function will return is a pointer to one of our like elements in the family tree, like one of our people. The variable, the value that it takes in, is generations. So in the very beginning, we're going to say we want to create 3 generations, but in just a second, we will see how that will be changing. Inside of the create family function, we first want to allocate memory for the new person. Right, we're starting from the very top of our family tree, and we're creating like sort of like the child, right? Like the element that will sit on the very top. And then after that, this is where the recursion happens, right? So if there are more than 1 generations to create, right? If generations is greater than 1, we wanted to recursively keep creating generations, right? And the recursion happens on lines 47 and 48, where I call create family within create family, but I'm just subtracting one generation at a time. So, for example, if on line like 41, I started with create family 3, right? Create family parentheses 3. I get to line 44, 3 is greater than 1. Therefore, I want to go inside of my if statement. And now I'm calling lines 47 and 48, subtracting 1 generation. So in this case, I'm calling create family 2, and I keep coming back to the top of my create family function until I don't have any more generations to create, and I go into my else condition where I sort of set my very bottom information, right? Like I'm setting parent pointers to null because there's nothing else to point to, right? There are no more like leaves on the tree, and I'm randomly going to assign alleles because obviously like these people don't have parents, so like they don't have any blood types to inherit. All right, so before we jump into the code, I just want to walk through this diagram to try to visualize it a little bit better. And someone asked what alleles are. So it is the blood type that you have. So for example, it can be like, it's like AB and then B0, etc. I'm not strong in biology, so I can't tell you more than that. But it is essentially just a blood type that you inherit from your parents. So this is sort of an already complete diagram, but let's try to walk through it part by part. So the very first node right here, right, like in generation 1, is our new person, right, is what we're going to create. And from the very beginning, it will not have any of its elements, right? It will just be an empty array of alleles and an empty array of parents. But what will happen next is I'm going to look at parents, square bracket 0, right? The very first parent element. And since this is where the recursion happens, I'm going to then create family again and end up in this part now, right? Where I create a person again, right? I'm creating a new node. I'm going to, again, go to this part, right? Like parent square bracket 0. And because I still have more generations to create, I'm going to go even one level further, right? Creating another person. At this point, I've already reached the bottom, right? Like this is my 3rd generation. And if I call create family again, that will be generation 0. There'll be generation 0. So this is where I want to stop, right? Like once I got to my 3rd level of people, this is where I want to stop. So I'm setting my parent pointers to null for both of them, 0 and 1 element. I'm setting them to null. For alleles, I'm actually going to pick them randomly because I don't have any parents to reference. So for example, it will be A and 0. And so then when I'm finished with this node, right, I'm going to go back up to generation 2. And then I'm going to say, okay, this case is closed, right? Like I've created my parent 0, and I can move on to now parent 1 and go through a very similar process where I am setting my parents pointers to null, I'm randomly picking the alleles, and I'm coming back up. So at this point, I've created pointers and filled those pointers up with information. So this part is done, right? I have 2 pointers that are referencing my parents, right? And they already have their alleles. We've set them equal to null. So the next step that is left is creating the blood types. And I can pick them depending on like what alleles my parents have. So between A and 0, I can pick 1, and then, oops, I think there is a mistake in my, okay. So it will be either A or 0 or B or 0, depending on what, what the program picks. And now that I'm done with this parent, right, I'm done with my whole part of my left tree. I've created these 2 parents, I've created these 2 parents. I can now use all of this information and come back to my very original node, and now I can sort of like close the case on my parent 0 because I've created this entire left part of the tree. I have my alleles, I have my pointers, like this part is done. And then I'm going to do a very similar, like exactly the same operation, but now on the right side, right? I'm going to go first to this person, then I'm going to look at their parents. I'm going to set the parents of those parents to null, fill out the alleles randomly, and then only once I am done with this person and this person, I'm going to bring it back up to our generation 2 person, fill out their alleles, and bring it back up again to the very first new person that we created. So it is definitely like harder to visualize, right, if we're just dealing with the code, But this would be a good step to take when you're trying to visualize recursion, right? Like what is actually going on is we're like pre-creating these empty variables or structures, and then we're going top to bottom until we reach like our base case, right? And in this case, our base case is, are we at the third generation? And if we are, this is where we want to stop, right? We're setting our parent pointers to null, we're randomly picking the alleles, and only after our base case part is done, we're going to bring it back up, filling up our tree one layer at a time until we again filled out each of those slots. So I definitely encourage you to try to draw this out on your own and try to trace the steps exactly. But now we're going to go back to the CS50.dev and try to code it together. So the first step that we have to do is to allocate memory, right? Every time we're going to create family, we want to malloc some amount of space. So because we're dealing with this new data structure called person, I'm going to create a new variable, new person, and I'm going to malloc exactly the amount I need. Right, so very similar to what we're just dealing in with the linked list, just creating a pointer to a specific data structure, in this case, person, giving it a name, again, variable name can be anything, and then mallocing an exact amount of memory we need. I'm going to just error check to make sure that the memory was allocated correctly. So if it is equal to null, I want to return 1. Okay. So, well, actually I'm going to return null because my create family function returns a pointer, so I can't return a number. All right, now that we took care of the first step, which is allocating memory, let's go into our conditions, right? So we just said that if there's still generations to create, we want to go into this if clause. And inside of the if clause, the create family function will keep calling itself recursively, right? But at some point we'll stop and we'll actually need to do some of the operations. And so what would that be, right? Like the very first thing that we talked about is setting the pointers. So if I'm looking at a variable called new person, right, my attributes are parents, and it is an array. So I want to index into 0 and set it equal to something. And then I'm going to do the same one for the second element, now indexing into 1. And what do I want to set it equal to, right? If I am at my new person stage right here, and I went into the if statement, and I've created family for these parents, this is exactly what I want to reference, right? Like if I'm the very top and parent 0 and parent 1 is like my parents, right? I want to make sure I'm keeping track of those pointers. So this is exactly what I'm going to reference here. So parent 0 and parent 1. Okay. Now that I've set my pointers, I want to assign alleles, right? And because I have parents, I can use their alleles to pick mine. So using a very similar syntax where alleles is an array, so I want to make sure I'm indexing into correct elements. And what I'm going to set it equal to is the information that is contained in these nodes, right? So parent 0 is just like a node of a person, right? And it has alleles, and it also has pointers to its parents. So I'm going to grab parent 0. I'm going to grab the alleles that that person has. Alleles. okay? But I want to pick them randomly. And the way that I can do that is using a rand function and using a modulo 2 operator. So let's break it down a little bit more. So if I have my parent 0, for example, this guy right here, and I am looking, and imagine this will be like A or 0 actually. So if I'm looking at alleles of this parent, right, I can pick between the two. So I can pick either 0 or 1. So to do that, I can just use a random function and it will give me like any number, like 28, 56, like doesn't matter. But using the modulo 2 operator, I will always get back either 0 or 1. So this will ensure some randomness in the way that we pick the alleles from our parents. Okay. Okay, so this is for the case if we have something like to pick from, right? Like this is if we keep creating our families and we have parents. But if there are no generations left to create, right? Like if we indeed have reached our base case scenario and there is nowhere to go to, we want to set parent pointers to null and randomly assign the alleles, right? What we talked about in our diagram. Well, we're still dealing with the new person variable, right? Because every time we call create family function, we'll create that new person. So we're going to go into the new person parents 0, set it equal to null. We're going to go into new person parents 1, set it equal to null. And then we're going to randomly assign the alleles because we don't have any parents to reference. So in a very similar way, we're first going to access alleles 0, then alleles 1. And then in order to assign the values, I'm just going to use the function that was actually already pre-written on the bottom that I will show you in just a second. Like that. So on the very bottom of our code is a function that's just randomly grabs a blood type allele and then will return it up top, sort of using the same logic, right? Just generating a random number and then using a modulo 3 operator to pick one of the 3. And that is because we don't have any parents to reference, right? So we need to do it randomly. And in the end, what I'm going to return is new person, right? So let's walk through this one more time. So because we're using this recursively, again, like it's sort of the same idea that we had with the linked list when we're using the for loop and the while loop, like we want to make sure that our steps inside of this like iterative process are very like standardized, right? We need to follow a certain logic. And in this case, it will be always allocating the memory for the new person, right? So every time we create this new person or a node or our tree, we want to allocate the memory. And then it is just setting some conditions, right? So if there are still generations left to create, we want to make sure that we're recursively calling this function, but also updating our values, right? So as I was showing on the diagram, like once I've reached the bottom and once I start going back up, this is exactly the lines of code that we're going to run, right? Like when we get to generation 2 and then our first generation, we're going to use these lines of code to populate our structs. And then our base case scenario, right? Like if there are no generations left to create, if generations is in fact not greater than 1, we're going to set our parents to null because there's no one else to reference, and we're going to randomly assign alleles, which are just blood type. Okay, and then every time I'm calling create family function, I want to make sure I'm returning the pointer to this person, right? Because I want to keep track of exactly where I am in the process. So let's try to make this to make sure we don't have any errors. Okay. Okay. So this is exactly right what we will get once we run the code. So our child, generation 0, is actually what gets created in the very, very last moment. What will happen first is these grandparents, then, and the biology of this might not be accurate, so if you're a biologist, please disregard. So first, these grandparents will get created, right? Randomly getting their blood type, setting their parent pointers to null. But when we get back to generation 1, we pick the blood type between the two grandparents right here, which just happen to be the same. And then we're still not reaching the child node, right? Like we're going into the second parent, going into his parents or her parents, and generating their blood types first. And then we're going back up right here, referencing this pointer connection. And then only after our grandparent layers is done, our parent layer is done, we're going to go back up to the child or generation 0 level and assign their blood types. Okay? So now let's get back to our last part, right? Like freeing all the memory that we've created. And here we will again use a recursive approach, right? So one thing that I could do if what gets passed into my free family is a pointer to P, I could have done something like free P, right? But the issue is that it's just the very first node, right? So I'm going to free the memory from my child, from my generation 0, and then I'm going to lose the connection to all of the other ones, and I'm not gonna free them properly. So what I'm going to do is utilize recursion. So our base case will be if P is equal to null, then we're done, right? Then we can return null, and we are just return, and we're done with this. But this is where we're actually freeing our memory. So let's free the child, which is easy. We just call free P. If we want to free the parents, we still want to reference this connection, right? So it will actually be free family. And we're going to grab the pointers to our parents. So calling free family on P parents 0 and P parents 1, right? So this is recursion because I'm calling free family inside free family, right? And then inside the argument that I'm passing in is just the reference, that the connection that we had. So my original pointer that I was looking at is P. Because it is a struct person, I have this reference to parents, and I can recursively call free family, freeing the parents until I get to my base case, which is when I know I am done, right? And the base case will be when we reach the parents. So if I keep calling P arrow parents 0, there will be a point, right, where I start on my very top node, I go P parents 0, it is not null, so then I go again P parents 0, this is also not null, so then I go P parents 0, and then I hit null in the very end, and this is how I know I freed that side of the list. So then I free parent 1, and then I go back up. And you can almost imagine these nodes or these people disappearing one piece at a time, just in the same way that we've created them one piece at a time, right? Because this is how recursion works. It will first sort of prearrange the structure, and then it would fill it back up with some information. But when we're freeing it, it's almost the opposite, because we first want to make sure we go all the way down, right, when there is nothing left to do, and then we go all the way up, freeing as we go. Okay? So let's make sure that we didn't make any errors. Oh, I did, semicolon. Okay, this looks good. Okay, I still get my family. All right, so this was a lot, and we've combined sort of like everything and all the abstract concepts that we've had of recursion, of linked lists, right, of memory, like all of these notions that are very abstract, that are hard to visualize, but I'm hoping the diagram and walking through the inheritance problem gave you a little bit more of understanding. But I would definitely encourage you to read through the spec by yourself, write this code once again by yourself, tracing exactly what is happening at each level of it all. But for now, let me pause and ask, what questions do we have about inheritance, linked lists, hash tables, or anything else that we've talked about today? Okay. Okay, so seeing none, so let me go back to the slides, and this is where we're going to sum up. Thank you so much for coming today to our section. I hope you enjoyed it, and see you next time.